All right, welcome back. So part two for the circular motion unit basically deals with universal gravitation. And so this is starting with these formulas here and going all the way up to this formula. Now, what is the idea behind this? Now, this is basically if there are planets or objects where we are given mass. As soon as you see mass, you usually know that there's going to be some type of universal gravitation question. So we have some units, some constants we can see here. G is 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. So every time you see big letter G, that's the value for that. And then we essentially, it's a similar idea. We have to look through the questions and figure out what it's asking and what we know, and make sure the units line up. We're just going to do a few examples here together. So I'm going to start. We'll just start with number one from assignment 2. All right. So number one from assignment 2 says Saturn has a radius of 60330 kilometers. I'm going to change it to meters right now. So times by 1,000 meters. And a mass of 5.7 times 10 to the 26 kilograms. Calculate the strength of its gravitational field. So basically, what is the gravity on Saturn? So, and the gravity can be given in meters per second squared, like an acceleration value, or you might see Newton meters. All right, or you might see newtons per kilogram. Okay, so we look at our formulas. And that is basically this this first formula over on this side. G is capital G m divided by r squared. So I'm going to use 6.67 times 10 to the minus 11. And definitely would save you a little bit of time to keep that number saved in your calculator somehow. Mass is 5.7 times 10 to the 26 kilograms. Divided by the radius squared. So 603,30,000 meters squared. And it has to be meters to cancel out correctly. So I'm going to be left with meter squared cancels, kilogram squared, one of them will cancel. So newtons per kilogram, which if you were to expand it differently would be meters per second squared. Okay, so doing the math here, 6.67 times 10 to the minus 11 times 5.7 times 10 to the 26 equals divided by 60330 squared equals. So G is 10.4456 and everything looks like it's 2 sig figs here, so G is going to be basically 10 newtons per kilogram. To do this to 2 sig figs over 1.0 times 10 newtons per kilogram. All right, and that's how to do the first formula. All right, we'll try number 6, which I believe is a Kepler's law question here. So an asteroid revolves around the sun with a mean orbital radius of twice that of Earth's. Okay, predict the period of the asteroid in Earth years to 2 sig figs. So they've given us everything we need here, but kind of in a bit of a roundabout way. So here's our sun, here's the Earth, and this radius is double that. So this asteroid is going around the sun. Forgive my circle, but basically if this is the radius from the Earth to the sun, we'll call this the Earth radius. The radius of the asteroid is 2 times the Earth radius. Okay. So the period of the Earth is 1 year. Right? That's how long it takes the Earth to go around the sun. The radius of the Earth, we may be asked to look it up. I don't actually think we need to, though. I'll show you why in a second. So radius of the Earth is just radius of the Earth. Radius of the asteroid is 2 times radius of the Earth. Okay, and we're trying to find how long the asteroid takes. So whenever you see two objects with radius and period, t and r, that is likely going to be this Kepler's law question. So we have t1 squared over t2 squared equals r1 cubed over r2 cubed. And this is the only formula where the units don't have to be in kilograms, or sorry, in seconds and in meters. Where the units basically have to be the same as each other. So if R1 is in kilometers, R2 will be in kilometers, okay? So do not have to be in seconds and meters, okay? As long as they're the same as each other. So T1, let's call Earth 1. So T1, R1, and this is going to be R2, T2. Let's see if we can do it without actually finding the Earth's radius, which we definitely could look up. T1 is 1 year divided by T2 squared. That's what we're trying to find, right? Basically T2. What is the period of this asteroid? Call it TA. R1 is the radius of the Earth cubed divided by R2, which is 2 times the radius of the Earth cubed. All right, and so we can see that this will actually cancel out. So 1 year squared is just 1 year squared, right? And then if you think about this, we have radius, 3 radius of the Earth's on the top, and we have 2 times, if I expand this just to show you, this is a particular example where they don't give us numbers. If they gave you numbers, you would just type in the numbers, but these will all cancel. So we're left with 1 cubed over 2 cubed. Okay, so finishing off this. So what do we have here? Well, we're trying to find TA. So if we think about cross multiplication, this TA squared is going to be 1 year squared times by 2 cubed divided by 1 cubed. So this is easy because this is all 1. And so I get a little cut off here. TA is going to be 2 cubed, 2 times 2 times 2, which is 8. TA squared, sorry, is going to be 8 years squared. This is what units we have here. And if I square root this, I actually get a number. So 8 square root is 2.8. So this takes the asteroid 2.8 years to revolve around the sun. Now this formula becomes easier when they actually give you numbers. If this was, let's say, 7,000 and this was 14,000, you could just very easily plug them in. And that would probably be a little bit easier, but I wanted to show you, sorry, it's getting blurry here. I wanted to show you how it works with variables. Because it's a ratio question, as long as we know the ratio between the two values, we actually can solve for a number here at the end. Okay, but just don't forget to square both sides and cube the other side. And then as long as the units match up, years and years, kilometers, meters, Earth radius, whatever we have, as long as the units match up, your answer will work out. Okay, let's look at number 10. So number 10 says, determine the speed and period of a satellite in orbit 265 kilometers above the surface of Mercury. Then determine the velocity with which Mercury revolves around the sun. Okay, so what do we know here and what are we trying to find? Well, it says determine the speed, so v, and period of a satellite in orbit 265 kilometers above the surface of Mercury. Now, whenever they give us these satellite questions, we do need to take into account the radius of the planet. So for example, if this is Mercury and this is our satellite, this is 265 kilometers, but we also have to figure out how far above the sort of center of rotation is this. So this is going to be the radius of Mercury, which they've given to us here. Radius is 2.4 times 10 to the 6 meters. And you see that that's much larger than 265 kilometers, so it actually becomes a very important value. So we have the total radius of the satellite. I'm going to add this right now. 2.4 times 10 to the 6 meters plus 265 kilometers is this many meters. So 2.4 times 10 to the 6 plus 265,000 meters gives me this value, 2665000 meters. That's the total radius of the satellite. Okay, I still don't know what formula I'm using though. Let's continue going. What else do we know? Determine the velocity with which Mercury revolves around the sun. So first, let's deal with the satellite questions. Well, what else do we know? We always know big G to the negative 11. And do we know the mass of Mercury? Yes, the mass of Mercury is given to us here, and that's a hint that we might need it. 3.2 times 10 to the 23 kilograms. Okay, so we're trying to find velocity and period, and so this is what we have to find it. So if we look at our formulas here, which one should we find first? Maybe the velocity? Let's find the velocity first. So, we don't care about force, okay? This might work if we're trying to find period. Actually, I think it will work. But we don't know period yet, so we can't use it to find velocity. There's actually no velocity in this formula, same here. So I'm going to use this one, right? So these formulas sometimes look a little bit complicated, but I've given you them reworked a few different ways. These ones are very similar, just rearrangements of each other. And the idea is that there's almost always only one that works. And if there's two that can work, usually they both will work. You know what I mean? So this is the only one that has mass, okay, and radius that you can find velocity. This mass is the mass of the central object. So if the satellite's orbiting Mercury, this is the mass of Mercury. Okay, that's how this works. So 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared times by the mass of Mercury, which is 3.2 times 10 to the 23 kilograms, divided by the radius, 2665000 meters. I don't believe anything's squared, nope, but the whole thing is square root. So this is where you just have to be careful with your math, with your calculator. 6.67 times 10 to the minus 11 times 3.2 times 10 to the 23. I think I typed that in wrong last time. Divided by 2665000 square root. There we go. Knew it looked a little bit large. So 2830 meters per second, which can be sig figged to 2800 meters per second. Sorry, I just made this, I typed this in as a 7, I believe, last time. All right, so we found our velocity. So now that I have velocity, a lot of formulas open up for me. I can definitely go back and just find the period with this formula here, okay? But because I have velocity, which formula can I use? I can just jump back to this first formula. So from the first section, 2 pi r divided by v. Now, people think because, okay, there's planets involved, I have to use G, or I have to use big G, I have to use this complicated formula. You can, but as far as this is concerned, the period doesn't care if it's a planet or a tetherball or a car, right? The radius and the velocity in this formula will give you the period. Okay, so once you have the velocity, you can just jump back to these easy formulas. 2 pi times the radius is this number again, 2665000 meters, divided by the velocity. I'm going to use 2830 just to give it a little more accuracy. And the period is 2 times pi times 2665000 divided by 2830. It gives me 5917 meters cancel seconds per revolution. And if we check our answer and check our sig figs here, this should be about 5,900 seconds. You could definitely change this to years or days or something, but there's nothing wrong with this answer. I believe in the solutions it gives it as 6,020 seconds, and that is simply if you plug in this value here. So that's how much the answer changes if you use the sig fig value too early. But if you're looking at the solutions, we plugged in 2,800, and that's what we get, the 6,020. But so it's about 6,000 seconds. Okay, we're talking a difference of 100 seconds because we took it to a couple extra sig figs in our answer. All right, and the last question I want to do is number 12. So number 12 says 2 spherical balls are placed at the center are 2.6 meters apart. Okay, so we have 2 objects and they are 2.6 meters apart. Okay, doesn't say what they are, but doesn't matter. The force between them, so they have a force of each other, is 2.7 times 10 to the minus 12 newtons. So a very small force, but it does exist. And what else do we know here? Determine the mass of each ball if one ball has twice the mass of the other ball. Okay, so we have to find M1 and M2. Now this is similar to the Kepler's law question we did a little while ago, where they could definitely give you just a mass in like kilograms. You have to find the other one, but they're making us think a little bit harder. So M2 is going to be 2 times M1, okay, and M1 is just M1. Distance is this. So as soon as you see force, okay, you should immediately jump to this formula. There's only one formula that has force, and that is G M1 M2 divided by D squared. So D is the distance between the 2 objects, and this is the formula for the force felt between two objects at a given distance. So they could be particles, they could be just hypothetical spheres, they could be planets, these could be really small or really large masses. This is the only formula with force. Okay, so when you see force, jump to this formula. We're trying to find masses. So this is our generic formula. In this question though, we want to change it so there's only one variable. So force is G M1, and then M2 is 2 times M1, right? That's specific to this this formula. So how can I simplify this? Well, force is 2G M1 squared divided by D squared. M1 times M1 just gives me M1 squared. Okay, so again, they might give you numbers. If there's numbers, you just plug in the numbers. This little rearranging is specific to this question because they're giving you the one mass in terms of the other mass. And I'm trying to find M1. Okay, so I'm going to rearrange this formula one final time here. M1 squared equals force times the distance squared divided by 2G. Okay, so now I can plug in my numbers. I'd rather do this. You can definitely plug them in here if you want to. So 2.7 times 10 to the minus 12 newtons is our force. Our distance is already in meters, which is fine. It's perfect. Squared divided by 2 times G. And eventually we have to square root this whole thing, right? So let's get an answer. 2.7 times 10 to the minus 12 times 2.6 squared equals divided by 2 divided by G. And then that's squared square root. So M1 is equal to 0.37 kilograms. That's one answer. And then M2, remember, was 2 times M1. So I just times it by 2 and I get 0.74 kilograms. So because they gave it to us in terms of the other one, we could do this kind of fancy algebra to find the answer, but be prepared to just plug in regular numbers. And again, if there's force, you're going to use this equation. And that's essentially it. So my advice for circular motion is ask yourself, are there planets involved? is there masses involved? And if so, then usually that requires sort of the second bank of formulas here. As soon as you see masses or force, you likely have to use these equations, sorry. If there's no mass involved, particularly if those questions usually don't have anything to do with planets, they will be the first formulas. But period is period, right? So if you need to find it using g and mass, you can find it here. If you can find it with r and velocity, you can use it here. Both formulas will work, okay? Same with velocity. It doesn't really matter if you can use both formulas. If you can use two formulas, usually either one will work. If you can only use one, that is your clue which one to use. And that's essentially it for circular motion and gravitation. Let me know if you have any questions.